So for the second part, I picked a much more obnoxious problem because I feel like it looks to me like some of the issues students are having are relating to solving complex valued matrices like this somewhat by hand. Okay, so the first thing to recognize is some of these coefficients are very nice and some of them are kind of a pain. So we want to simplify down what we're trying to do as much as possible. All right. So the first thing we want to do is figure out what's going on the right-hand side here. Okay, so we want to convert these phasors to complex numbers. So the first entry here is 4. Second entry here is 8 at an angle of 120 degrees. Um, and so actually, I'm going to pull. Okay, so we can do the same sort of calculations I did in MATLAB. So that's going to be 8 times e to the power of, I'm using Google, so I'll have to say I times uh, 120 times pi over 180. Okay. Um, and so this is something like 8 at an angle of 120 is minus 4. I should actually ask Wolfram Alpha for this, because then it will at least give it to me in radical form, which you can do. This is a standard trig identity, so you can figure out sine and cosine in terms of radicals. I know it's going to have a root 2, so that's 8. So it's like, yeah, so it's specifically, it's minus 4 plus 4 radical 3 j for us. And then if I take 120 at an angle of I times negative 150 pi over 180, or sorry, I put 120, not 210. Okay, so the next row gives us minus 105 radical 3. Can you tell my parents are math teachers? Literally, the voice in my mind right now is my mom's voice saying radical 3. So, negative 105 rad 3 minus 105j. Of course, she would be saying I here. All right. And then our bottom number here is just 0 at an angle of 0. All right. So the first move we want to make is start clearing out things. Our annoying coefficients are down here on V3 and V4. So we're going to use row operations or back substitution in order to eliminate from the bottom two rows. We would like to eliminate V1 and V2 as quickly as possible. All right. So in our bottom rows here, there's a J35 in front of V1. And what's nice about this row right here is V1 is the only component in this position. So if I take the top equation and multiply it by J35, then I'm going to get J35. And on the right-hand side, for angle 0, we know it to be 4 from up here. So on the right-hand side, we're just going to have 4 times 35, which is 120 plus another 120. So this should be 140. J. Also conveniently for us, in the last row of this equation, there's a 0. So I'm going to take the J35 and the 140J, and inside here are 3 more zeros. And I'm just going to subtract that from the fourth row. So if I subtract this from the fourth row, all of a sudden our bottom, this becomes 0. And this cell is now just going to contain negative 140J. And if we convert this back to angles, negative j is an angle of negative 90. And so this is equal to 140 at an angle of minus 90 degrees. Okay, so it's just subtracting 35j times the first row. So we get negative 140j, which corresponds to 140 at an angle of negative 90 degrees, if we want to write it that way. But up here, we're just replacing 0 with negative 140j. So we'll write that over here, negative 140j. Okay, so our bottom equations, we've fully eliminated V1. Now all we want to do is eliminate V2. Now, V4 is going to be modified when I do this, but otherwise it's not really going to be a big deal. If we look at the second row now, I've got a 35 to clear. This is currently in the form of minus 1, so I'm just going to multiply it by 35. So if I take the second row and multiply it by 35, I'm going to get 0 minus 35. I'll be more careful here. 35. And I'm going to kind of use augmented matrix notation real quick. Okay. And so I'm multiplying this thing up here by 35. And that's fine. So that's going to be negative 140 minus 140. I'm out of space, of course. So that's minus 140. Oh, and it's actually going to be plus. We'll put the j here, and then this is 140 radical 3. If I'm using Wolfram Alpha, you can use your trig circle. Pull out your trig unit circle. At an angle, it's the calculation for example, the second row would be 8 cosine of 120 plus j sine plus 8j sine of 120. So, sorry, the calculation for this right here is done. It is 8 times, I'll use parentheses, cosine of 120 degrees plus j sine of 120 degrees. Pull out your unit circle, and those are known things. And they give you negative 4 plus 4 radical 3j. Okay. On the unit circle, the angle 120 is up here. So the cosine component is the one that's exactly half of the 8, but it's negative, so it's negative 4. The sine portion is positive, and it's root 3 over 2 times 8, so 4 radical 3 j. All right, so I'm just multiplying regular 35 through because that's what I need to clear. So I get a negative 35, a positive 35, and then these 140 terms here. And so I'm trying to clear the 35 from our third row now. So I didn't change the top row, so the top row is still 1, 0, 0, 0, 4. My bottom row is now 0, 0, 20 minus j7, minus 1, or sorry, minus 20. Minus 28j. And then this side, again, is minus 140j. Pretty easy. So I'm taking the third row and I'm adding 35. Oh, I don't want to. put this in here. Okay, so I didn't need to write either of these pieces. I wish I could pick this up and move it. Okay, I don't actually want to change the second row, but we'll just leave this in place. And so then I'm taking this and I need to add it to row 3 in order to cancel the 35. So we don't really care about the form of our upper 2. We can just use these original upper 2's at the end. It's fine. Um, what matters is eliminating 2 variables from the bottom 2 rows. So after I add this modification of the second row to the third, there's now a 0 here from minus 35 plus 35. This has no effect on the value in the V3 slot, which is still negative 10 minus J14. And I'm going to change colors because I'm going to run out of space. And so then I have this gap here, okay? And I'll just fill in what goes there. So that's 10 plus J14. We're adding a positive 35 to it. So this is just going to become 45 plus J14. Which is fine. And so then I need to take the element here, and we're adding it to the element here. So comparing our real parts and our imaginary parts, this is going to be slightly ugly too, but it's certainly calculatable. So I have to add the real parts of each of these. So this is just going to be minus 105 radical 3 minus 140, whatever that is. And then the J component is 140 rad 3 minus 105. J. Okay, so if we're not going to use MATLAB now, we're going to invert a 2 by 2 matrix. And I should have just given myself as much space as possible. So we're going to invert a 2 by 2 matrix. So our 2 by 2 matrix has the value negative 10 minus J14. This entry should be 45 plus J14. Okay, this entry is 20 minus J7. This entry is minus 20 minus 28J. Okay, the remaining thing is now that it's a 2 by 2, the inverse of a 2 by 2 is really easy, at least by comparison to other things. So to find the inverse of a matrix, okay, we want to invert this. All right, so the inverse of the matrix is 1 over AD minus BC. So we have to calculate negative 10 minus J14 times negative 20 minus 28J. And it's minus BC, so this is going to be minus 45 plus 14J times 20 minus J7 Then in the matrix, we swap the positions of A and D. So this is going to be minus 20, minus 28J. Down here is the negative 10, minus J14. Then I'm supposed to take negative B and negative C. So this is going to be minus 45 plus J14. And then this is negative 20 minus J7. Okay, so you put minus signs on the main diagonal, or sorry, you swap the order of the main diagonal, then you put minus signs on the off diagonal. So from here, it's a matter of calculating this, what's in the denominator, kind of making a mess of things. So that was just minus 140J. Okay, this goes in here. I'm trying to keep this in exact form as long as possible. Of course, you can approximate all of these things, right? You can make this an approximate form. Just keep it out to a number of decimal places. It's fine. So we need to calculate whatever is going on in the denominator. You can absolutely manually run this through, but I'm just gonna, oops. Yeah, so I'm just gonna calculate. So that's like negative 10 minus 14i times negative 20 minus 28i. Then I just go minus quantity 45 plus 14i. And so your calculator can do this times 20 minus 7i. Okay, so that denominator is exactly, in this case, this denominator is exactly, okay, this is not where I want to put it. So the denominator, which I'll put in a new color. Uh-oh, the colors are starting to get annoying. So the denominator here is minus 190 plus 595J. Okay, so we're going to take 1 over this. All right, so we're going to call this value capital D. So we're going to calculate 1 over D. Okay, we're going to call this value capital A. And we're just going to call negative 140 capital B. Okay, this is going to be 1 over D times, all right, so this is going to be A. I'm now just multiplying. Okay, so out here we have 1 over D times this coefficient matrix times the two pieces on the right-hand side. So this will give us our solution. So we get A times negative 20 minus 28J plus B times negative 45 plus J14. I'm really hoping this works the first time so I don't have to go back and try to dig up an algebra error, but that could happen. And then down here we get A times negative 20 minus J7 times A plus B times, the other coefficient here is minus 10 minus J14. Whatever these numbers are V3, V4. And at this point, they'll probably be approximates. And then you just hop back up here and back substitute. So we can see that directly V1 equals 4 angle 0. Up here, you'll obtain the value for V4. So you'll just plug in the value for V4 right here. That'll be a known quantity. This will be minus V2 plus V4. Has to be equal to minus 4 plus 4 rad 3J. Whatever V4 is, drop it into this equation. Drop in 8 at an angle of minus 20 as a complex number. So you just add V2 to this side. So you would just take V4 plus 4 minus 4 rad 3J. That'll be your V2. That's what it wants you to plug in. V1 is 4 angle 0. So if everything worked out, I'm going to ask Circuit Tutor if, oh, but I need to calculate these values. Okay, so I'll calculate those by hand. Give me a second. I still made calculation, but I just realized I didn't write a minus 140J here. Okay, 1 second. Algebra mistake here. So when I wrote down the matrix that I needed to invert, I inverted the real part and then I forgot to invert the imaginary part. So I need to change the signs on, I mean change the signs. So the negative of 20 minus J7 is negative 20 plus J7. And if I negate 45 plus J14, it has to be minus 45 minus J14. Okay. Okay, and then I need to carry that over here. So there and there. That's now a plus, that's now a minus. Okay, so if I calculate the first pieces here, I'm getting that the, oh, 1 sec. Okay, ready to continue. So the calculations of these parts lead me to okay, so then I get that V3 is equal, oh, V3 is equal to negative 1.375 minus 11.244J. Then, okay, so I am actually calculating these directly. So I keep pausing long enough to punch it into the calculator. So V4 is equal to, again from direct calculation, oops, minus 3.574 plus 1.24. Oh, oops, 2.406. And then for V2, I have to back substitute the value for V4 into this equation for V2. Okay, so after back substituting V4 in here, we get V2 as being equal to 0.426. The next digits are 0, 1, so minus 5.688 J. And then we still have that V1 equals 4 angle 0. So if I wrote that out, we would just say V1 equals 4, real number. So I'm going to take these three numbers and we will convert them back to phasor forms. Give me just a second. Okay, so cleaned up the slide here. So these are our results. So these are fairly straightforward to convert over. So we get that V1 is 4 angle 0 degrees. That one's pretty simple. So for the rest of these calculations, we do the absolute value. So for V2, we're going to calculate the square root of 0.426 minus, or squared, plus the square of the imaginary part. So that's 5.688 squared. Okay. And so then for that calculation, I'm getting, okay. So that appears to be 5.704. Okay. We would like our angle. So to get the angle, we're going to take the arctangent of imaginary over real. So since the imaginary part is negative 5.688, and the real part is 0.426, then if we calculate that out, this should be, what did I get? I got negative 85.72 degrees. Okay, so that's our V2 in the form that circuit tutor wants. For V3, we calculate the square root of 1.375 squared plus 11.244 squared, which I'm getting as approximately equal to 1.33 or 11.33. To get our angle, I wanted to write these out because we have to be very careful. Arctangent of imaginary over real will give us negative 11.244. Oops. Over, whoa, okay. Sometimes it's just a, okay. Divided by the real part, where'd the mouse go? Which is negative 1.375. Okay. If you convert this to degrees and plug it into circuit tutor, this is wrong. Arctangent has a limited range because the tangent function is not one-to-one. The arctangent will always return an angle between What is it? It returns an angle between 0 and 180 degrees, I think. Um, no, it's just in the right half plane. So the arctangent returns the angle in the right half of the unit circle for a positive real component. Yeah, so it produces a result um, between minus 90 degrees and 90 degrees. But because this has a negative real part, that's not the correct angle. The angle you're going to get here is going to be in quadrant one, so the upper right side, where both it gives you the angle that would be represented by positive 11.244J and positive 1.375. We need the angle in the third quadrant. So the corresponding angle in the third quadrant, we actually have to take 180 degrees um, plus this. I'm going to use minus 180 degrees plus this because of the form um, that it wants. So it's going to be plus or minus, we'll just say it's plus or minus 180 degrees. It doesn't matter which one you do, you will get a legal angle. The only issue is that Circuit Tutor expects your answer to be between minus 180 degrees and positive 180 degrees. So if you're not in that range, you just add or subtract a 360 degrees in order to get to the range. But you can also resolve that by choosing positive or negative 180 carefully. You just have to go to the other side. It's the supplementary angle, or that's not the right term, but it's the angle that's 180 degrees away from the angle that you get here. So after that version of the calculation, so this will produce a positive angle, and we've got to take it, we do minus 180 degrees so that positive minus positive becomes a nice negative angle that is still larger than negative 180. If this arctangent gave you an angle in the fourth quadrant, we would want to add 180 to land in the range that Circuit Tutor wants. But this is the first quadrant angle, so we subtract 180 to get the third quadrant angle. And so our third quadrant angle is negative 96.97 degrees. Okay. Again, we have another negative real part here. So when we go to calculate V4 and we do our square root, we're going to get 3.783 as the magnitude. The angle is 160.9 degrees. That is calculated as 180 degrees plus, so we need, this is a second quadrant complex number with a negative real part and a positive imaginary part. So this angle's in the second quadrant. Arctangent gives us an angle in the fourth quadrant. So we go tan inverse of imaginary over real is 1.241 over negative 3.574 is the correct modification to get 160.9 degrees. The arctangent is going to give you 19 point or negative 19.1 degrees. That's in the fourth quadrant, but the actual correct location is in the second, so we add 180 degrees to get the angle between 180 and minus 180 that corresponds to this second quadrant complex number. So if you plug those values in to Circuit Tutor, it confirms that these calculations are correct. And so that's how you would solve this system of matrices. You absolutely can, one at a time, just RREF it. So in a general matrix, you would just, the general process would be if you have arbitrary coefficients, okay, you can set up an augmented matrix if you want. And so all you would have to do is you might rearrange your rows to put an easy one up in the top left, but ultimately what you would need to do is get a one in the top row, and it doesn't matter what else is going on over here. Then you multiply the top row by whatever you need to cancel out the coefficients a, b, c. So you take the first row times negative a and add it to the second row. Take the first row times negative b and add it to the third row. Take the first row times negative c and add it to the fourth row until 1, 0, 0, 0 is here. Take the second row and you need to somehow get a 1 here. So if there's a coefficient you can divide by to get a 1, that's great. If there is no 1 here, one of these other two rows, if the equations are unique, one of the other rows has to have it, has to have a 1 somewhere. So you would maybe shift a row into place to get a 1 here, but then whatever the coefficients are here, alpha, beta, and gamma, you then multiply the second row by negative alpha, add it to the first, multiply the second row by negative beta, add it to the third, multiply the second row now by negative gamma, add it to the fourth, so that your matrix now looks like 1, 0, 0, 0, 0, 1, 0, 0. Who knows what's in these other ones? You've got to get a 1 here next by either shuffling the last two rows or whatever you need to do. Then multiply this by whatever you need to clear these coefficients, and your ultimate goal, keeping your augments all along, eventually when you arrive at 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, whatever's on the augment is your solution. So that's your V1, V2, V3, and V4. After you RREF this, and my V1 looked a little weird, so we'll shift the one over. Okay, and so if you go out to, 4 or 5 sig figs, you won't calculate too many compoundings, sending you out of a plus or minus 1% calculation. If you calculate to 3 or 4 or 5 sig figs, 5 is probably too much. 4 sig figs should get you there. You can just punch your way through this without too much trouble. Um, but probably the practical way is to get a 2 by 2 matrix in two of the variables um, by just eliminating if you can eliminate two variables from the other two rows, yeah, if you can eliminate two variables from two rows, you can condense the remaining two rows into a 2 by 2 matrix, invert it, get your final values for those variables, and then you back substitute them into the other equations, and you can get, if you needed, you would, in general, you might get another 2 by 2 that you would invert, but that's probably not going to happen. You'd be better off RREFing than doing that. Generally, with these problems, you're going to have easy coefficients for two of the variables, so you can probably eliminate them from the complicated KCL rows and invert it. But that's the way this runs. Hopefully it helps. Have a good weekend, everybody. Have a good day whenever you're watching. Okay, bye bye.